All right, so we're going to start our next cluster. So we're moving on to a new topic here. Just base your answers to questions 26 through 30 on the information below and on your knowledge of Earth and space sciences. Some questions may require the use of the 2024 edition reference tables for Earth and space sciences. So our topic is the origin of our solar system. It says the sun and 8 planets in the solar system formed at the same time. Evidence of their formation can be found throughout the solar system. Scientists have used data from planets, meteorites, and Earth to determine how the solar system formed in its early history. The data table below lists some information for the 8 planets. So we have our terrestrial planets that they listed for us: Mercury, Venus, Earth, and Mars, the number of moons that they have, Jovian planets, Jupiter, Saturn, Uranus, Neptune, and the number of moons that they have as well. Okay, so we do have, just thinking of my reference table, I do have a solar system data table that is in our reference table in case we were to need that for anything. Okay, so I'm going to look at I'm just going to kind of think about my planet types for a minute. So just as a reminder, our planets are separated based on their characteristics. So our terrestrial planets, our first 4 are like Earth. They are more rocky and solid. Our second 4 planets are Jovian. They are more gassy. So I'm just going to write that because it's something that I might need to remember. So rocks, and these are made of gas. Okay, and my sun is essentially right here. Really low the nest, okay? All right, 26 says, which statement best describes the differences between terrestrial planets and Jovian planets in the solar system as a result of the early history of their formation? Okay, the first one says, terrestrial planets have longer periods of revolution and fewer moons than Jovian planets. Okay, so longer periods of revolution, fewer moons. Those are my 2 characteristics. And so longer periods of revolution, I might have to go to my data table, but moons, they definitely gave me right here. So I'm going to look. So terrestrial planets is what they're talking about. And they said they have fewer moons. So if I look, I see that terrestrial planets had 0, 0, 1, 2. So terrestrial. And my Jovian planets had 80, 83, 24, and 14. So that is true. Terrestrial planets had fewer moons than Jovian. So that is true and checks out. So I'm going to put a little check mark there. And then for longer periods of revolution, I need to go to my reference table. So I know that terrestrial are the first 4, Mercury, Venus, Earth, and Mars. And so I'm going to look for period of revolution, which is on here. Right here, period of revolution. And I'm going to highlight my first 4, Mercury, Venus. So there's Earth, and then there's Mars right there, compared to my Jovians, which we used blue, Jupiter, Saturn, Uranus, and Neptune. Okay, so now I can make that comparison. So I have 88 days. So these are in days, or here's 2 years about. These ones are 11.9 years, 29.5 years, 83.7, 163.7 years. So these are much, much longer. So my Jovian planets actually have longer periods of revolution. So this is not true. So that gets rid of answer number 1. Number 2 says terrestrial planets have greater densities. So terrestrial planets, greater densities, longer periods of revolution, which we just looked at here, right? That's not true. So we're not going to choose that one because we just proved that that was not the case. 3 says terrestrial planets have larger diameters and are closer to the sun than Jovian planets, okay? So closer to the sun, I know that. Those are my first 4, so I'm going to say, yep, that's good. I'm going to check that off. Larger diameters, I need to come back to my reference table. So terrestrial, again, my green ones. I'm going to look at equatorial diameter here. There's Mercury, Venus, Earth, Mars, and then Jupiter, Saturn, Uranus, Neptune, okay? And again, on your regions, you can write all over this. So if you want to circle things, label, put T's and J's, you are welcome to do so. And so if I look, I see that these numbers are much larger than these numbers. So my terrestrial planets, my green ones, are actually a lot smaller than my Jovian, which are much bigger. So I'm going to write terrestrial planets were small and my Jovians were big based on their diameters. And so this says terrestrial have larger. That's not true. So I can get rid of that one. So 3 is not my correct answer. That leaves me with number 4. Okay, 27 says which value would be the most accurate prediction for a period of revolution for Saturn? Okay, so again, I would not know this off the top of my head. I'm going to need information from somewhere. And so I'm probably going to need to use this data table that was given to me in my reference table. So it wants to know period of revolution for Saturn. And I look to see that in my answer choices, their units they gave me are days for all of them. So I need to know how many days it would take. So I'm going to start by looking for period of revolution data. And I find that right here. We were just looking at this column. And the planet they gave me was Saturn. So I'm going to be looking in this right here where they cross. So 29.5 years. Okay. So that is great, but it does not give me days. And I know that my question gave me days. So I have to think about how many days are in a year. And remember, our year is based off of Earth's period of revolution. So Earth's revolution, if I look here, is 365.26 days. Okay, so I can use that to help me figure out how many days it would take for Saturn to orbit. So I can say, okay, Saturn takes 29.5 years times 365.25 or 26 days per year. And I'm going to hit enter and I get 10,775.17. So I'm going to look for that answer. And the closest value would be number 2. Okay, so introducing another resource for us. Meteorites on Earth have been helpful in reconstructing the history of our solar system and our planet. Samples taken from meteorites have been age dated using absolute dating techniques that measure the amount of uranium-238 compared to the amount of its decay product in samples found on Earth. The graph below shows some information about uranium-238. So we have a graph showing radioactive decay. And we are looking at a meteorite. Okay, so we have percent remaining. So this was our, remember we always start with 100% of radioactive material, and over time it is going to decay. And we know that our half-life, so the amount of time it takes for half of the material to decay, is what we use to find age. Okay, and so for half-life, we have to know how long it took for 50% of the material to disappear. So if I look here, percent 50, and I come over and I come down, my half-life for uranium was 4,500 million years, okay, which equates to 4.5 billion. So my question says, a sample of a meteorite was tested and found to contain 50% uranium-238. Use evidence from the graph to make a claim about how the radiometric dating of meteorites can be used to construct an account about when Earth formed. Okay, so we know that meteorites and Earth were formed around the same time, or we assume they were formed around the same time, that all of our solar system was kind of formed at that same time. And so if we were to find out how old this sample was, we need to use the percentage. They told us that the sample contained 50% of uranium-238. And so if I go to 50 and follow it down, we got that 4,500 as our number. And so that tells us that Earth must be 4,500 years old, because we assume they were formed around the same time. So we might say something like 50% uranium-238 would make the meteorite 4,500 million years. So Earth must also be, must have formed. Sorry, I know this is not the best here. 4,500 million years ago. Okay, so we're using the age of the meteorite to assume that that's when Earth had initially formed. Okay, and our next question, our last one, says throughout Earth's history, meteorites have created impact craters on continental and ocean crust surfaces. However, of the approximately 200 craters confirmed on Earth's surface, only about 20 are located within ocean crust. This is surprising since approximately 70% of Earth's surface is covered in water. It is suggested by scientists that the movement of Earth's plates may play a role in the lack of evidence of impact craters observed on ocean crust. The approximate rates of movement of oceanic and continental crust are indicated in the model on centimeters per year. 2 impact craters are labeled. Okay, so remember, Earth is unique because we have a lot of things happening on our surface. It's very dynamic, and so because we have that liquid water, those plate tectonics, a lot of the evidence of our early history has been erased over time, and so we have to look at other planets, other surfaces such as the moon, to kind of study what we think happened in Earth's early history. Okay, so we have impact crater A. This is the one they're talking about. And then we have impact crater B that they're talking about. So we have 2 here. And then we have kind of the model of what's happening. So we have a seafloor spreading ridge, which is where we have divergence. So our plates are moving apart in this direction. We can see that here. We have these arrows moving out. And then we have convergence coming together. It says, which statement most accurately identifies why evidence of impact crater A will most likely not be preserved for as long as impact crater B. So we have to think about what's happening to the crust. So here we have a trench where subduction is happening. So if we look, we can see that over time, this crust that impact crater A is located on is going to be sucked underneath this crust over here. So this is going to be sucked in and destroyed. Whereas impact crater B, this crust is overriding. So this crust is going over the ocean floor, and therefore it is not being destroyed by subduction. Okay. So it says impact crater A is located on faster moving ocean crust and will be destroyed by subduction. So we know it'll be destroyed by subduction. We just talked about that. So impact crater A. But I'm going to check the rate. So it says crater A is located on faster moving ocean crust. So if I look, impact crater A 7 centimeters per year, impact crater B 2 centimeters per year. Okay, and so A is faster moving, so that is true, and it will be destroyed by subduction. So I can actually get rid of a couple of these. If I wasn't sure what process, I could get rid of some of these just by looking at the rate. So it says crater A is located on a slower moving plate. 7 centimeters per year versus 2 centimeters is not slower. Impact crater A will be destroyed by hot molten rock at the mid-ocean ridge. The molten rock is coming up. It's actually moving out in this direction, so that is not true. And impact crater A will be destroyed by eruptions from the nearby volcanic arc. Not so much, right? So that's happening kind of way over here. So 1 is our best option for that question. Okay, we actually do have one more question. So it says, Earth systems do not operate independently. For instance, changes in the ocean's temperature can influence atmospheric temperatures. A similar coevolutionary process occurred in Earth's early history with oxygen levels were transitioning from Earth's ocean to the atmosphere. So I actually think this is kind of a standalone question. So they don't have it kind of starting a new cluster, but I think this kind of, don't really think it fits super well with the ones above. So it says, the model below shows some information about Earth's ocean and atmosphere. So we have how ocean has changed in the, how oxygen has changed in the atmosphere. So I'm going to use yellow for that. So this is our oxygen in the atmosphere here, this level, this line. And then we have our oceanic oxygen, which they've described here in this little bar here. And then we have our life processes, which we will do in red. And those are down here. Okay, and then we have time. Just identify the process that caused the ocean levels in Earth's oceans, or oxygen levels in Earth's oceans and atmosphere to change. So that's the first thing we have to do. We have to identify what process caused ocean levels to change. So let's look at, I'm going to highlight this in blue. So we're talking about ocean levels and the atmosphere. And so we're going to look at where the change started to occur. So we see in our atmosphere that our change starts to happen right about here, right? So it stays pretty steady, and then all of a sudden you see this rise, and it just continues to rise. And our ocean goes from no oxygen to mostly oxygenated. So this is where our change happens. And so since it's talking about coevolution, so it told us up here that things are kind of changing together at the same time. I'm going to look at that link, right? So we know that oxygen and the ocean and atmosphere changed here together. And so I'm going to think about what would have caused that. So I'm going to look at this life column. So we have Earth forms first life in oceans right about the same time that our oxygen levels begin to rise. We have a life event that occurs, okay? It says photosynthetic organisms up here. And so our process we have to identify is photosynthesis. Okay, so photosynthesis is going to be the process. And then we have to argue, kind of support our claim here. We're making this claim that photosynthesis is what caused oxygen levels to change. And so arguing with evidence means we have to explain why that would cause this change. Okay. And so photosynthesis is when organisms consume carbon dioxide, and as they consume carbon dioxide, they are going to release oxygen. Okay. And so we have to identify both pieces here because it talks about how the photosynthetic organisms right here are going to be in the ocean still, right? So we want to talk about how the ocean organisms produce oxygen during photosynthesis. Okay, so that's going to release oxygen to the oceans. And then we just kind of want to talk about like how that would have changed, right? So like what change did that lead to? So we know that the photosynthetic life caused the rise in oxygen. What was the result of that? So if we keep going, we can see that after oxygen levels began to rise, we then had a great diversity of life forms. Okay, so it allowed for organisms to become more diverse. Okay, so ocean organisms produce oxygen during photosynthesis, raising oxygen levels, which allowed for more diversity of life. Okay, so again, co-evolution. Co means more than one. Okay, so if we just stopped at the sentence that stated that we produce oxygen during photosynthesis, we are not supporting the idea that there was a co-evolution of two different spheres. Okay, and so we want to talk about the biosphere in terms of life. We're talking about how that's changed our ocean levels, our atmosphere levels. We have to recognize the other piece, which is the more diversity, in order to get to kind of hit that piece about coevolution.